make a start on today's lesson, which is the binomial to normal approximation. So as you can see here, I've got a binomial distribution at the moment. So here I have n as 20 and the probability as 0.5. So you could think of this as you flip a coin that's fair, the probability of getting heads is 0.5, and you do this 20 times. And here we're showing all the outcomes. So as you'd expect, 10 is the most likely of outcomes. You flip the coin 20 times, you'd expect to get 10 heads the most amount of times. But 9 and 11 would also be quite frequent results. 8 and 12 less so. And then obviously you've got 7, 13, 6, 14, 5, 15, and so on. Now we can see here that when we've got a probability of 0.5, we've got this perfectly symmetrical distribution here, which if I overlay a curve on top of it, then hopefully we should see that actually this looks very much like our normal distribution shape. Okay, so we can see it has similar properties there, that in the middle we've got our most frequent value. Now remember, with normal distribution, the median and the mean and the mode are all the same. And also we have this symmetry here as well. So we can see that given the right conditions, we'll talk more about those conditions in a second, given the right conditions, we can see that the binomial distribution can be approximated by a normal distribution. Now, one little disclaimer I will say is I'm aware that you can do pretty much all these binomial problems that we're going to do today. I'm aware that you can just do them with binomial CD on your calculator, or even binomial PD when you've got a particular value on your calculator, rather than have to make some approximation. The reason why we're doing this is that it used to be that you couldn't just do it on your calculators, so it's something that's kind of remained in the spec from older times. But also sometimes if you're like programming something, it's useful to be able to approximate it with the normal instead. For example, when I teach core maths, we learn about normal distribution, but we don't learn about binomial distribution. So I had to actually use what we're doing today to translate a problem that was binomial into one that was normal so that we could do it. So bear with me that sometimes you might be thinking, why are we doing this? We could just do this with binomial. You know, it's a lot of good reasons to do it, and also we can check as well. Right, so we can see here that the distribution nicely fits this normal distribution curve here. Now, as I make n larger, this becomes even better as it refreshes. So you can see if I make n really large, so 100, then we get an even better representation of this binomial distribution that fits this normal distribution curve. If I make n small though, we can see that it's a bit off. Okay, so generally speaking, we want n to be a large number. Now when we say large, there's no kind of right or wrong answer for what n is large. Basically, the bigger the better here. Typically we'd say about 20 or larger, but it does depend on the situation. Another reason for using the normal to approximate binomial is if we've got a probability that's close to 0.5. Now here you can see when the probability is 0.5, we have this perfect symmetry for our binomial distribution. If I make that 0.2, however, then it's nowhere near as good of an approximation, and you can hopefully see that the 4 and the bars of 3 are quite similar in height, but then 5's a fair bit shorter, 6 shorter still. So really we need to be close to 0.5. We can kind of drop to between like 0.4 and 0.6, but we've got to be quite close to 0.5. And yet again, there's no right or wrong number. It's just the closer the better. And also what we could do is we could make the probability a little bit further away if n is a bit larger to compensate for it. Okay, so if you have a really large value of n, then you probably can drop it down to 0.4, 0.35, and so on. Now, the last thing I want to talk about with the curve here on my GeoGebra file is that obviously binomial distribution is discrete, whereas normal distribution is continuous. So let's say you just want to work out the probability that x is 12. Okay, so just highlight that bar there. Now with binomial, you just work out the probability that x is 12. But with normal, we can't work out individual values because it's continuous. Because with normal, you can have 12, you can have 12.00001 and so on. So if you're working this out with normal, what you'd have to do as an approximation is work out the probability between 11.5, the lower bound of 12, and 12.5, the upper bound of 12. And then let's say I want to work out the probability that it's between 7 and 12. So I'm including 7 and I'm including 12. With normal distribution, we'd have to think about that as going down as the 6.5 and then going up to the 12.5. But this is what's known as our continuity correction, and we'll talk more about this later. So if you've got any questions so far, I just want to put them in chat. I'm just going to switch my screen in the meantime, and then we'll go through the examples. Okay, so what we kind of learned there was because normal distribution is symmetrical, binomial is a good approximation when the probability is close to 0.5. Okay, because if the probability is 0.5, then you have this perfectly symmetrical distribution. If it's near to 0.5, then you almost get that symmetry. Okay, low values like 0.1, 0.9 aren't going to work. And then also, if n is large, the approximation is good. And yet again, large is quite ambiguous here, but generally speaking, 20 or larger is better here. Greater than 20 is generally good enough. Now, when we switch from binomial to normal, with binomial, we have n and p, okay, the number of trials and the probability of success. With normal distribution, we obviously have our mean and variance. Now, to work out the mean, all we have to do is just do the number of trials times the probability. And by the way, these two formulae here, you will get in your formula book. Okay, so the mean and how we work out the mean and how we work out the standard deviation from the binomial, you will get these given in the formula book. For the mean, we do the number of trials times the probability. And this makes sense. If you think, go back to flipping a coin 20 times, if the probability of getting heads is 0.5, on average, you'd expect to get 10 heads there. Okay, you do it 20 times, you've got half chance of success, times them together, and that will tell you the mean number of heads that you'd be expecting. So to work out the mean, just do n times p, the number of trials times the probability. It might not be quite as clear where the standard deviation comes from, but what we have to do here is we do the mean, so np, times 1 minus p, which is the probability of failure, okay, 1 minus the probability of success, and then we square root that to find the standard deviation. Okay, so np times 1 minus p would be the variance, and then the square root of np times 1 minus p is the standard deviation. But you get given this in the exam. Okay, you get given it in the formula booklet. Okay, so you will have to look it up in your exam, but you do get given this. Right, so on to our examples here. So I'm going to go through 3 examples. I'm going to give you a chance to do the past paper question at the end yourself, so you can have a go at something as well. So firstly, we've got a biased coin. So the probability is, so it's not fair. The probability is not 0.5 of getting heads, whereas the probability here is 0.53. The coin's tossed 100 times and the number of heads x is recorded. So we're going to write down a binomial model for x. So first off, we write x, our squiggly line, and then b, capital B for binomial, and we write the number of trials, which is 100, and the probability of success, which is 0.53. So explain why x can be approximated with a normal distribution. So my first question of the day, why can we use the normal distribution to approximate this? So there's two reasons why I can do this. Just want to tell me in the chat. Okay, excellent. N is large. Okay, so 100. We're classing that as a large number here, and the probability is close to 0.5. It might not be exactly 0.5, and it's, you know, rarely always going to be exactly 0.5, but it's close. Okay, so we just say N is large, and the probability is close to 0.5. So now what I'm going to do is I'm going to write down the model that I use for my normal distribution. So firstly, I use the fact that the mean is n times p. So all I do is n is 100 and p is 0.5. So I just do 100 times 0.53, which just gives me 53. Also, for normal distribution, I need my standard deviation, or I need my variance. So to work that out, I use the other formula that we were given. And here I just do n times p times 1 minus p. So 1 minus 0.53, times it all together in square root, and I get 4.99. Okay, remember here I could have actually just wrote 53 times 0.47 because NP obviously is just my mean, which I worked out from before. So in terms of my normal distribution, I'm going to use a different letter here. I'm going to use the letter Y here. For a normal distribution, let's put capital N. The mean is 53 and the variance is 4.99 squared. Remember, with normal distribution, you write variance there, not standard deviation. But typically, it will help to write the standard deviation squared there, just because you'll often be using that when you put it in your calculator later on. Now, I mentioned earlier that there's one of the main differences between binomial and normal is that binomial is discrete and normal distribution is continuous. So for that reason, we need to apply what we call a continuity correction. So if you look at this first example here, okay, so where I've just put a star there. If, for example, you work out the probability that x is greater than 5, well, that means in terms of our binomial distribution, we'd be working out the probability of 6, the probability of 7, 8, 9, all the way up to 14. Okay, n is 14 here. So in this case, if you look at how I've shaded the bars in, now when we switch it to normal distribution, what we don't do is just work out the probability that it's 6 or more. Because normal is continuous, we want to think of every individual number as having a lower and upper bound. So for example, the number 6 there has a lower bound of 5.5 and an upper bound of 6.5. So actually, when I'm working out the probability that it's 6 or more in terms of binomial, or just more than 5, I'd have to work out in terms of normal the probability that y is greater than 5.5. So I hope you can see from the bar here, the lowest value it can go to is 5.5. Okay, so the first value we include is the 6. So in terms of normal, that goes between 5.5 and 6.5. So you just work out the probability that it's greater than 5.5. Now, remember, it is an approximation, so normal would actually assume it's possible to get 15, even though you only got 14 trials in the first place. But if you've got those conditions that n is close to 0.5 and n is large, then you should find that the probability of getting something like 15, 16 numbers out of our range are actually very small. Then our second example, we've got the probability of x equals 9. Now, with a normal distribution, you can't, as I mentioned earlier, you can't just do work it out for an exact value with normal distribution because it's continuous. Okay, the number that's less than 9 is just 8.9999, and the next number up from that is 9.00001, for example. So to work out the probability of exactly being 9, when you switch it to normal, you want to work out the probability that's between 8.5 and 9.5. So I'm going to go into our second example, and hopefully we can see this in action now. So firstly, I've got a binomial distribution here, and I'm going to approximate it with the normal. So first things first, I need to find both my mean and my variance or standard deviation. So just remember the mean, that's NP. So we do n, which is 150, times p, which is 0.48. And I get 72. Okay, so we're saying if we do this 150 times on average, we expect to get 72 successes here if the probability is 0.48. And then we also need a standard deviation. So we would just do the square root of np times 1 minus p. Remember, this is in your formula booklet. So np, well, we just worked that out, that's 72. 1 minus p, that's 1 minus 0.48, that's 0.52. And when I get that, I get 6.119. So that means in terms of my normal distribution, the mean is 72 and the variance is 6.119 squared. Now for the first question, we're asked to work out the probability that x is less than 70. So what I'm going to do is I'm just going to draw a few bars like this. Now you can just draw a number line if you want to, but I'm just going to do this to show what's happening here. Okay, now obviously there will be many other bars than this, but I'm just kind of focusing in around the area that we want to actually solve our problem. Now, if I'm looking at the probability that x is less than 70, with binomial, it's discrete, so I wouldn't include that bar of 70, but I would include the 68, I would include the 69, okay? And also, of course, I include 67, 66, 65, and so on. So in terms of normal distribution, the problem I'm trying to solve is what is the probability that y is less than 69.5, okay? So it's not just a case of if x is less than 70, y is less than 70. If x is less than 70, I need to do y is less than 69.5. Now with normal, less than or equal to or less than doesn't matter. It very much matters with binomial, but it doesn't matter with normal. So here I can now just work out this problem with my normal distribution. So this is where I get onto my calculator and I go to normal CD. I put a lower limit of something like minus 1,000, and then I put my upper limit 69.5, put in the mean and standard deviation, and then you should get 0.341. If anyone needs a reminder on how to do that on your calculator, then do let me know, please. Right, okay, so the second question asks us to work out the probability that x is between 80 and 90. Now, when I switch this to normal distribution, what I want you to do is in the chat, can you put in what is my lower bound and upper bound for the normal distribution? Okay, so for binomial, you'd have 80 and 90 is between. But with normal distribution, what is my lower bound and what's my upper bound? Or is there anything you need me to kind of go over again? Let me know if that question doesn't make sense. Okay, great. I can see some answers coming in now. So we've got upper of 90.5, lower of 79.5. Excellent. Yeah, fantastic. So I could draw a little sketch. The bars that I'm drawing, doesn't really matter about the height of them. Okay, and if you prefer just to do a number line, then just do that. So with this, I'd be... just helps me show what I'm including, what I'm not. So I wouldn't include the 79, but I would include the 80. I'd include the 90 and the 89 as well. I would include 91. So hopefully I can see there with the bar of 80, I can drop as low as 79.5. With the bar of 90, I can go as high as 90.5. So on my calculator, I put a lower limit of 79.5 and an upper limit of 90.5. Simply work that out on your calculator and you should get 0.10923 significant figures. The final thing I'm going to do today is go through this plenary question, and then I'm going to give you a chance to go through that past paper question on your own, and we'll do a little recap as well. So finally, just to do one final example to kind of make sure we're all clear on this before we go today. For a particular type of bulb, 55% will produce yellow flowers. A random sample of 80 bulbs is planted. Calculate percentage error incurred when using a normal approximation to estimate the probability that there are exactly 50 yellow flowers. Okay, so hopefully we can see here the idea of this problem is we'll see that it's not an exact answer that we get when we approximate it, but hopefully we do get something that's quite close is what we should see. So firstly, I'm going to write my binomial distribution. I've got n as 80 because the sample is 80, and the probability that produces a yellow flower is 0.55. Now, first off, I'm just going to work this out for binomial, okay? So, yeah, again, I'm aware that really, in reality, we'd just do this and we'd leave the question there. We wouldn't bother approximating it to normal. But the idea of this question is just to show you that the approximation does give you something that is fairly close. So if I want to work out the probability that x equals 50, I'm looking at exactly 50. I'm looking at a particular value. So I want to use binomial PD, okay, not binomial CD. I want to use binomial PD here. So on your calculator, you go mode 7, binomial PD, and then you'd put in n is 80, probability of 0.55, and we should get 0.036518. I'm going to go to more than 3 significant figures here, because when I'm working out my percentage error, it's going to be quite heavily persuaded by this, like even the 4th and 5th decimal places here. Okay, so that's what the probability would be in terms of binomial. What I'm going to do now is work it out in terms of normal. So mean is going to be n times p, so it'd be 44. So we're saying out of this sample of 80, on average, you'd expect 44 to produce the yellow flowers. For standard deviation, we do np, so that's 44, times 1 minus p, 1 minus 0.5, so 0.45, and then square root it, and I get 4.45 when I do so. So this means my normal distribution is going to be a mean of 44 and a variance of 4.45 squared. Okay, again, in the chat, can you put down for my normal distribution what my lower and upper limits are going to be here? So I want to work out the probability it's exactly 50. What's my lower and upper limit? Or, do I need a lower and upper limit here because it's exactly 50? Do I need that lower and upper limit? And the answer there is yes, I do. I need to go between 49.5 and 50.5. I can't just put in exactly 50, the normal distribution. I need to go between 49.5 and 50.5. So I do that on the calculator. And I get the following. So now I need to work out my percentage error. Okay, so hopefully you can see for both of these answers I've got here and here, they are quite similar. Okay, to three decimal places they are the same, or to two significant figures they are the same. So if I'm working out my percentage error, what I need to do is work out how far away the approximation is from what the exact answer is. So I need to do 0.036185, my approximated answer, take away my actual answer. I think this is what sometimes confuses people. We've done similar things like this when we've done like binomial problems as well. You need to do the approximated answer, take away the exact answer, and then we divide that by the exact answer. Working out percentage error as well is really important if you do science as well. You should be doing quite a lot of this in science as well. And then we times it by 100, and we just get 0.912%. Okay, so I believe you should get 0.00912 as a decimal. Just times that by 100, we'll get 0.912%. And that's our error. So we're just under 1% out doing it this way. Now, I mentioned that do let me know in the chat if you've got any questions, by the way, anything you're not sure about. I'm just going to kind of go on to what to do next then. So I'm going to leave this question out for today, but the answers are there in your assignment. So I'm going to give you a chance to have a little look at that one yourselves, and then just check the answers through the assignment. Just be careful when you do this question that you don't just work out the probability. You don't just do inverse normal with 71 or more is 0.0401. Make sure you still use your continuity correction here, because what you should notice is when you're talking about the binomial, you're using H. So just because the probability of H is greater than or equal to 71 for binomial, when you go to normal, make sure you use a different number there when you do that one. Okay, but you will have to use standard values for that one. So I'm going to give you a chance to have a bit of a think about that one yourselves, and do let me know if you do have any questions about that. I'm happy to kind of do further videos on that if it's needed, but I'm trying to keep this as half an hour today. So key points for today: we can go binomial to normal if n is large and the probability is close to 0.5. To go to switch it up to your normal distribution, you need a mean and you need standard deviation. So for your mean, you do n times p, and for your standard deviation, you do n times p times 1 minus p and square root it. Also, binomial is discrete, normal is continuous, so you will need to use a continuity correction there. Draw number lines, draw sketches to work that out if you're not sure. For this lesson now, have a look at exercise 3F and have a look at the following questions there. The ones we want to see are 3 and 7. So have a go at those ones, and please upload those ones. Make sure that you've caught up on anything that you haven't done. That includes Friday's work of the binomial quiz. That's just the Microsoft form. If you haven't done that already, just also be aware that I believe the answers say they want it as 4 decimal places, so make sure you read that carefully. Please ask questions if you're not sure about anything, and I will upload the video for the log start question shortly. So it's just a 5-minute video going through the answers to that if you want to find out how to do that question, because I know a lot of you struggled with in particular part B. I'm going to end the chat, end the stream in about a minute, so I'm going to end the recording here, but please let me know if you do have any questions.